So everybody can hear me all right in the back? Okay, sounds good. So welcome to Chemistry 20A. I assume this is your first chemistry classes you're taking at UCLA. If you search for it, you'll probably hear like terrible stories about this class, like it's being super hard. Yes, it is hard in its own sense, but it's not going to be undoable. So let's just look at the syllabus together and get some idea about what this course is going to be. One of the things you should know is I added everybody onto the Canvas site. So double check if you have your access to Canvas or not, and you'll find all information, all the course materials, video recording, announcement. I'll post everything on Canvas. You should be able to find everything there. So in here, we'll start from the syllabus. As you can probably see, I already posted a syllabus quiz. So that's going to come available after this course. So go ahead and take the quiz. That's a 5-point extra credit. So by just reading the syllabus, you should be able to get all those 5 extra credit, all right? So 5 free points at the beginning of the class. I hope that's good enough for you. So looking at the syllabus, let's look at it together. First of all, we have all the information. I'm Huiling Shao. I hope you already know it. That's my email address, and that's my office hour location and time there. If the time for the office hour doesn't work for you, feel free to just shoot me an email or just send me a message through Canvas, and we can arrange some other appointment that works better for you. All right. For this course, you'll also be taking discussion sessions with your TA. So discussion sessions are super important to make sure you're successfully pass this course. So do take a note that discussion session will begin week 1. So this week you'll have discussion session already. So make sure you show up into your discussion session this week. We'll probably also have learning assistant present in discussion sessions. So if you're taking classes in the fall quarter, you probably already have been working with some of the learning assistant. But basically, they're like just undergraduate students who take the course, they're successful in the course, and they're going to come and help you to go over the materials in the discussion session with your TA, of course. For the course materials, this course is part of the inclusive access. So if you're opt-in for inclusive access, you should be able to get access to the textbook. I also posted a link to the textbook in our Canvas site. So try that out and make sure you have access to the course materials ahead of time. All right, and here comes to the point that everybody is most interested about, right? How is this course graded? So as you can see here, the first part, when we see the Cengage chapter end, homework assignment, those 20 points are just free points, I promise you, because every question you get 10 times to try it. And after each try, if you got it wrong, it's going to show you how to correctly answer that question. And they're going to give you a different version to try it out. So those 20 points are just free points for you to take. So for now, make sure you go to the Cengage website. It's also on the Canvas module. It says do this first. So click that link, go there and try to do some play with it and get to know what it feels like. All right, so these 20 points are just free points. They are free in one sense if you started early, but I have to warn you, these Cengage assignment can be really, really long. For example, for our first chapter, chapter 4, the average time my previous students spent on the Cengage assignment is 8 hours. So that means 8 hours divided into 3 weeks, right? So don't wait until the last minute to start your Cengage assignment. So just start working on it, and if you get it wrong, that's okay. It's going to show you how to correct it, but don't wait until the last minute to finish it. And then we have the collaborative worksheet. So that's going to be graded by your TA in your discussion sessions. So again, it's discussion session, right? So these worksheets, you can work with your friend, you can work with your TA, you can ask questions about how to answer them. So this part, I do expect the average of these collaborative worksheets to be above 90. So you can work together. You don't have to struggle alone. If you're lost, you can ask your TA about it. So these 50 points, those points are if you work for it, you should be able to get it, right? It's not hard. And then we have the exams. So midterms and finals will all be open book, open note. It might be take home or in person in the lecture hall. I haven't decided on that. But the bottom line is all the exams will be take home exams. So do not spend your time in trying to memorizing any of the equations, try to memorizing any of the materials in the class. Instead, spend more time just thinking about what is the physical meaning behind it. How can I better approach a problem? All right, don't try to remember anything. Like I have students coming to me and say, how can I remember the periodic table? You don't need to. You will have it available for you. You'll have equation sheet. You'll have all your notes and everything. I'm using the standard letter grade policy for all the UCLA students. And note that this class is not being curved, but if the class average is below a B minus, I may be like prompt everybody's score up, so the average is at B minus. So that's only gonna work for you. It's never gonna work against you. All right, and regrade policy. So this part is basically saying after every exam, you'll have a week to go over your graded exam and try to figure out, did we miss something? Or is there anything you're having question about? So you have a week to work on that regrade problems. All right, and I'm just gonna go over, well, these are just general things for COVID and academic integrity. I'm not gonna speak too much about it. You know what to do. I mean, just be honest and do not copy. I mean, it's open book, open note, right? So trust yourself, not your neighbor. Okay, and then we're coming to the course schedule. So for the course schedule, I color-coded a little bit. So here is what the color code means. Whenever you see something green, that means that that's a holiday. There's no class on the holiday. Whenever you see something blue, means it's an active class. So for active class, means like you're just gonna come. I recommend you print out the blank note on Canvas site. I'm gonna show you a little bit what it looks like. And once you print out that blank note, we can work on the problems together, like equation derivation, or just work on complicated problems together. So that's what those blue color codes mean. And then before each exam, I always arrange a buffer day. So that means like if I got slow on some of the topics or everybody got confused on say, what is the Schrodinger equation? And then we can use that buffer day to go over the material before your midterm exam. Okay, and that's everything from the syllabus. So do go back to the syllabus, read it a little bit, and do the syllabus quiz. I mean, it's 5 free points. All right, and before we jump back to the actual material, I have one more thing to talk to you about. So on the Canvas side, on the left-hand side, you can see for every lecture, I have 2 sets of notes. The first set is called a blank note. It means like I'll leave it open. Some of the questions is like not answered. So we're gonna go over it together in the class. We're gonna go over the blank note together. You'll also see, like for example here, that's a blank note, right? So when we're talking about units, that's just blank. So we're gonna work on that together. But I'll also post an annotated note after each lecture. So that means in the class, if you have time, if you need to choose, am I gonna write this down or am I just gonna listen and try to understand? Just listen and try to understand. I'm gonna post all my recording. I'm gonna post all my annotated notes. So that's an example of an annotated notes, right? So that's what we're gonna go over in class together. So it's gonna be posted. So don't worry about writing down everything when I'm talking about it. Okay, and now we're ready to get back to talk a little bit about chemistry. I'm gonna pause here and see if we have any administrative questions. Yes?
Yeah, I'm not sure if I heard correctly, but about the exams, you had mentioned that you're gonna decide whether they're take home or in class?
Yeah, so exams are always gonna be open book, open note. It might be take home, it might be in person. I haven't decided on that yet. I'll get it to you in like 2 weeks before the exam. All right, so getting started to the actual material for Chemistry 20A. So this is gonna be a like rough outline about what we're gonna talk about in this entire quarter. So this is the introductory chemistry course. We're trying to answer some very fundamental questions about chemistry. That being said, we're going to start from the very, very fundamental question, is what is a particle, right? Electron, it is a particle. So how are we going to describe that particle? Once we know the quantum mechanical description of a particle, I'm just going to write it down here. We're going to start from a particle. And then we'll start looking at what is an atom. So everything before midterm 1, we're just asking the very, very fundamental question, what is an atom? We'll just spend lots of time. You'll feel like, why am I here? This is not a chemistry class, it's a like math class or physics class. But trust me, like these builds up the foundation of a more modern definition of an atom. So once we know what makes an atom, we can move on to talk about what makes a chemical bond. All right, so you put two atoms together, you have a chemical bond. What is the nature of that chemical bond? We'll have classical description of a chemical bond, and then we'll have the more modernized quantum mechanical description of a chemical bond. And once we're done with that, we're done with midterm 1 and midterm 2. At the end, we can look at spectroscopy, chemical reactions, or in general, we now know what is the nature of an atom, what is the nature of a chemical bond, and we're ready to work on some more complicated systems, well, chemical reactions or transition metal complexes and so on. So that's a general structure. But for today, we're not going to talk about quantum mechanics. Today is an easy start. We'll just start from the very basic things. Namely, we're going to start from units. So we all see this sign a lot. We're in the United States. But one of the things is I didn't grow up in the United States, right? So here we all know that is the unit of that is miles per hour. But one of the problems is from where I grew up, I treat like the speed will be like kilometer per hour. And since we know 1 mile equals to 1.61 kilometer, so if we're going to translate that 65 miles per hour into kilometer per hour, basically what we're doing here is a unit transformation, 65 miles per hour times 1.61 kilometer per mile. And we can cancel out some of the terms, and we get roughly 105 kilometer per hour. Super simple. Just basically you need to cancel out the unit when you're doing the unit conversion. I mean, you can do it faster way. I just like to write out the unit to make sure I didn't get it wrong somehow. And in scientific, the inconsistent use of unit can sometimes cause more serious problems than speeding tickets. So if we look at, this is one of the LA Times that was published back in 1999. I hope it's a little bit more evolved now. So what the story reads is Mars probe lost due to simple math error. And what that math error means is whenever you have a miscommunication between scientists who design the aircraft and also they design it in the meter system. Alternatively, when you actually send it to the manufacturer, to the engineers to build the aircraft, what they did is they used the English system, so like inches, miles, and so on. And because they did that calculation wrong, eventually that spacecraft is just lost, and that's just sad, all right? So we don't want that. Whenever you're doing a math problem in this class, make sure you're using the consistent unit all along the way. Okay, so that's a cartoon version. So how do we avoid that from happening again? So that we want to introduce the new SI unit, or International System of Units. I say it's new because this International System of Units has only been recently updated in 2019. So previously, the definition of these units, of these fundamental units, are based on like physical objects. We'll see some examples there. But now in the newly defined SI unit, what we have of all these units are depends on universal constant. So in the inner circle, we have universal constant. So in the inner circle, that's our universal constant. And on the outer circle, we have the unit, the new SI unit. So what are these properties? So here, meter, that's length. And seconds, that's a unit for time. Ampere, that's for electric current. Kelvin, that's for temperature. Mole, that's for the amount of substance. And then we have the luminescence, intensity, and also mass. So we'll be looking at some of the more relevant units for this course. Namely, we're going to focus a little bit more on length, mass, and also amount of substance. The others, we'll just leave it there. As long as you know there's a connection between the unit and the universal constant, and then we're good. So let's look at length together. So here, when we're talking about length, the old definition, again, is depending on a physical object. Say the old definition means a meter is 1/10 millionth of the distance from North Pole to the equator. So it's depending on some kind of physical object. And there's the obvious problem, right? So this is a meter bar that's distributed by NIST, or the National Institute of Standard Units. It is really good. I mean, it's a palladium iridium meter bar. It's made in 1960, but it's still a physical object. The problem was using physical object as your fundamental definition for unit means these physical objects can change along the time. It can erode. I mean, the surface can change when time passes. So now the NIST recently updated the definition for unit. For example, the new 2019 definition for length is stating the meter is now defined by taking the numeric value of the speed of light in vacuum. Is 2.9979245 times 10 to the 8th. Like, you don't have to remember it. What you want to know is you want to know that C, or speed of light, is a universal constant. All right, so that's the take-home message. Now the new unit system use universal constant like the speed of light to define unit, to define meter. Or in the other way we can put it, as we have universal constant. So in this case, we're talking about length. So the universal constant corresponding to length is the speed of light in vacuum. And we normally abbreviate it as C. The universal constant is connecting to the SI unit, which is meter. And we abbreviate it with M. And in between, you can imagine we have physical laws that's connecting them. All right, so the take-home message again is now in the new definition for unit, we're talking about universal constant and unit. They're connected by physical laws. So for the length, we're using the speed of light in vacuum as the universal constant to define it. Moving on, likewise, we have mass, or the weight of an object. That's, again, a fundamental physical property of any object. So before, in the old definition, the kilogram is the mass of 1 liter of water. Again, it works for a long period of time, but it depends on some kind of physical property. So that's why in 2019, we updated to have the kilogram is defined by taking the fixed numerical value of the Planck constant. So Planck constant, H equals to 6.62607015 times 10 to the negative 34 kilogram meter square per second, or joule second. We'll talk more about the Planck constant on our Friday lecture. Okay, so so far we talked about length, meter, and speed of light. Now we have kilogram, mass, and also the Planck constant. And the third unit we're going to be talking about is amount of substance, or mole. So in this case, 1 mole of substrate, so 1 mole, so what mole here acts as a unit. By definition, it contains exactly Avogadro number of elemental entities. So Avogadro number, again, it's just a universal constant. That's by definition, Avogadro number equals to 6.2214129 times 10 to the 23 per mole. So how do you understand mole? Mole, basically, you can imagine it as a bridge between when we're talking about a macroscopic mass and also microscopic number of atoms. So in this case, we're just saying, for example, we have 12 grams of carbon. So that's effectively saying we have 6.022 Avogadro number times 10 to the 23 number of carbon atoms. All right, so let's look at a simple example together. We have a scratch of paper, we can work on it together. So, say now we have 5 grams of sulfur dioxide. Can we calculate the number of moles and number of molecules of sulfur dioxide in this 5 gram? So this is effectively the similar problem we did when we were translating that speed unit. So if we look at it, here we're talking about the number of moles. So what we need is we know the mass, and mass equals the number of moles times molecular weight. So here N is number of mole, and the molecular weight, sometimes it's just abbreviated with MW. So the molecular weight of sulfur dioxide, that equals to 32 for sulfur, plus 16, that's for oxygen, and we have 2 of them, 64 gram per mole. You can also write it as like gram per mole. It's the same. All right. And then the first question asks for the number of moles. So N equals to M over molecular weight. That gives you 5 grams, 5 gram over 64 gram per mole. I normally just put the unit there and then I cancel it out. It gives me an idea about if I got the unit right or not. So in this case, we're ending up with 0.078 mole. So if your end unit is correct, then you know you have the correct answer here. Likewise, we can do the same for number of molecules. Now we know the number of moles, the number of molecules. We just use that N times Avogadro number, which is 0.078 mole times 6.022 times 10 to the 23. And we have these units cancel out. It's about 4.70 times 10 to the 22 molecules. It's not hard, you just need to pay attention to the unit, that's all. All right. And one last thing when we're talking about unit is unit for energies. I mean, unit for energies, that's not part of the SI unit, the fundamental SI unit we talked about, but it's important. We use it a lot in chemistry. So in general, when you're looking at only the SI unit, then we'll probably have that in joule. So 1 joule, that's 1 kilogram per meter square per 1 kilogram meter square per second square. So it is a very big unit because we're talking about kilogram, meters, and everything. But if we're talking about atomic level, when we're talking about just several atoms or electrons, then it's just too big to deal with atomic size problems. So sometimes we'll also use electron volt. So electron volt, that's being defined as the energy of a single electron gains upon being accelerated by an electric potential of 1 volt. So 1 electron volt. That equals to 1.609 times 10 to the negative 19 joules. I'm not going to question you about why that's the case, but you need to know how to convert between these energy units. Say you never see it before, but you need to know how to convert between these units. So one of the example questions is if we have the gas constant. Normally we have the gas constant in 8.314 joule per Kelvin per mole, and how to express that in electron volts per Kelvin per mole. Again, it's a unit conversion problem. So the way I write it is I just say R equals to 8.314, write out the unit as well, joule per Kelvin per mole, times 1 electron volt. It's 1.609 times negative 19 joules. We can cancel out the units. That gives you 5.167 times 10 to the 19. Electron volt, Kelvin, mole. Or you can also write this part as electron volt, Kelvin, whatever you like. I mean, both ways works. Okay. So, any questions before we move on to the next topic for unit and everything? Okay, seems like this part is easy enough for everybody. And now we're moving on to talk about the periodic table. All right. So, actually, let me just change the setting a little bit. Just keep a periodic table up there. Okay, I'm just going to keep 2 periodic tables on the side, so when I'm writing on my notes, you also get an idea about what the original table looks like. So in chemistry, we use periodic table a lot, right? When we're talking about periodic trends, what is an element? What exactly are the properties of those elements? So what I want you to know is not to remember everything, but again, you need to know how to get information from the periodic table. So reading it, it's a very dense table with a lot of information. So we're just gonna go over it in 4 different ways. So the first way, let's look at the center one, all right? So this is a zoom out version of what that is. I'm just gonna zoom it really out for you. So in here, we have the atomic number. So that's how the elements are being organized in your periodic table. So atomic number, oh, my pen looks really big up there. Atomic number, or we sometimes abbreviate it with Z. You'll see that symbol Z when we're talking about Bohr model and everything. So that tells you the number of protons in that element. That means in the nuclei, how many protons are there. And then we have the vertical ones. So these are called groups. So when we're looking at group, when we say group 1A, group 2A, group 3A, when we're talking about the vertical columns when we're saying group. So you need to know, like, for example, this is group 4A, right? It's written down here. That's group 4A, group 5A, or like group 2B, 1B, that's for transition metals. And then, if we're looking at the horizontal direction of the table, we have the period. So if we're talking about period 1, that's hydrogen and helium. Period 2, that's lithium, beryllium, boron, and everything. And at the end, we have something called the characteristic group. So that's the color codes showing on the bottom of the table. So when we're talking about an alkali metal in period 3, so you need to know what we're talking about, right? So an alkali metal, that's this color. Period 3, that's sodium. And one last thing here is we have the mass, atomic mass of the element. So that's the average mass of that atom. So what do I expect from you? Again, I hope you can get useful information from the periodic table. So one of the examples, this is not going to stand alone as a quiz question or exam question, but it will be part of it. Say, can you find the atomic mass of some kind of halogen in period 3? So it's asking for atomic mass for a halogen in period 3. So look at it, period 1, 2, 3, and that's my halogen. So we're talking about chlorine. All right, so you need to know how to read the table and to get information out from it. And we zoom it out, and we get the mass to be 35.453. Or when you're writing it down, you can see the answer to this question is going to be chlorine. Or you can write the symbol Cl, that's also correct. And it's asking for the atomic mass. That's 35.45 gram per mole. Okay. But here is having something that's peculiar because we have an atomic mass that's not even an integer number. So the reason behind the atomic mass being not an integer number are when we're talking about isotopes. So we're moving on to talk about atomic mass and isotopes. So in the periodic table, when we're looking at the atomic mass, we're taking consideration of all the isotopes of that element. So in general, isotopes are forms of elements that they might have the same number of protons. So the Z will always stay the same for that element. But it might have different numbers of neutrons. So neutrons are just particles, they're neutral, they're in the nuclei, it doesn't have a charge, but it can change your atomic mass. And just to give you an idea, I mean, here are the mass of proton, neutron, and electron. And what we can see here is proton and neutron have roughly the same atomic mass. I mean, roughly the same actual mass, but the electron is way lighter comparing to both proton and neutron. So in this case, we're saying electrons are light enough. Are light and do not contribute to atomic mass. All right. We'll spend a little bit more time on isotopes. So here, in general, this is more or less a nomenclature thing. Let me turn the periodic table back. this is more or less when we're a nomenclature, so how to write the symbols for an isotope. So in general, that's what we have. And this X, that gives you the chemical symbol. So again, this chemical symbol is always correlated with Z. Whenever you have Z equals to 1, that will always be a hydrogen. And then A gives you the mass number, means Z plus any number of neutrons. So look at the example, again, taking hydrogen as an example. In hydrogen, Z always equals to 1, but it can have different numbers of neutrons. So the 3 isotopes for hydrogen is, well, start from hydrogen, that's the most abundant one. Write down the natural abundance. This one is like 99.999% of hydrogen atoms are just hydrogen. If we read it, it basically tells us it has 1 proton. So 1 proton correlates to its being a hydrogen, and then 0 neutron. Or we can have deuterium, that's H2, 2H. Contains like 0.001%. And if we look at it, that's going to contain 1 proton, 1 neutron. All right. And the end, you should have also trillium. That's 3H. So in nature, when we say it's trace, means like we can somehow know it exists, but it doesn't contain any statistical importance. So this has 1 proton and 2 neutrons. All right. And one of the simple questions about isotopic effects is we can look at how to calculate the relative atomic mass, which is the atomic mass we show up in the periodic table. So again, we're taking the chlorine as an example. So it's given that chlorine elements always exist in 2 stable isotopes. So say in 1 mole of chlorine, we have 75.8% being chlorine 35. And the other 24.2% is chlorine 37. So if we're calculating the relative atomic mass, we're taking the 75.8% times 34 plus 969 plus 24.2 times 36.966. You do the calculation, you get it to be 35.452 gram per mole. And that's the relative atomic mass we see in the periodic table. Okay, so that's all I have about the periodic table for now. We'll can come back and talk about the periodic trends when we finish talking about basic quantum mechanics. See if we have questions before I move on. Okay. And then I want to start talking about some of the old atomic models. And I want you to think about it, like why it is wrong. So this is a question we have. So Rutherford's planetary model, that's one of the older model of atomic structures. So in this model, what people are imagining is you have negatively charged electrons that's circulating the positively charged nuclei. Because the motion is a circulating motion, you can imagine these electrons to have some kind of angular momentum. So in this case, we say this model is wrong for obvious reasons. It doesn't even fulfill the classical physics model. So let's think about it, like why that is wrong. one of the things you can think about is these accelerating electrons. So I can tell you one of the physical laws. So according to physical laws, it's all charged particles with some kind of acceleration or momentum. Or just momentum in general, will release electromagnetic radiation, which is a form of energy. So now maybe somebody can take a guess why the Rutherford model is just wrong, just even from the classical physics point of view. So we know two pieces of information. The first piece is in this model, the electrons are accelerated, right? Has some kind of angular momentum as circulating the nuclei. The electrons are charged particles. And even according to classical physics, we know that charged particles with acceleration or with momentum is going to release electromagnetic radiation, which is a form of energy. So why we say this model need to be wrong? Yes?
Yeah, it's supposed to be stable.
Yes, more or less, but when we're talking about atoms supposed to be stable, we're saying the electrons are not going to be sucked into the nuclei, right? So the reason this is wrong is because in the process of circulating, in the process of these electrons having angular momentum, it is continuously giving off electromagnetic radiation. So when we're looking at it, because it is giving off electromagnetic radiation, and we know the energy need to be conserved. So because the energy need to be conserved, that electron is keep losing energy. It's keep losing its kinetic energy. And eventually you would expect that electron being sucked into the nuclei. And that is why this model is just wrong, even when we're talking about the classical model. So that's just a beginning, right? We're just talking about some of the older model and why that is wrong. And the next lecture will have some mathematical background and also some physics background, just to get you prepared. All right, we're going to talk a little bit about calculus. Again, this is not a math class. I'm not going to ask you to solve any derivative or integration, but you need to understand the physical meaning of a derivative. You need to understand the physical meaning of an integral. And also, this is not a physics class, so you're not going to solve a wave, but you need to know what I'm talking about when I'm saying wavelength, frequency, amplitude, and everything. So next lecture, I hope I can get you prepared and get ready for those terms, know the physical meaning of those terms. And Friday, we'll start talking about quantum mechanics. All right, and thank you, everybody. Remember to take that survey. It's just free points, 5 free points.